Homework 3.4, the rational zero theorem, zeros of polynomial functions, video 6. Homework due Wednesday, May 27, 2020 at 11:59 p.m. I didn't list any problems on this one, but if I had to, I'm going to use my red marker if I can find out where I put it. I'd lose my head if it wasn't attached. I would say, excuse me, questions 5 through 7 and questions 11 through 14. I'd like to do a full-blown example of what I call a stone-cold problem. I give you a problem and no hints. This is based off of a certain number in the homework. Let me find it. It's number 11. It actually gives you some suggestions, but we'll be using the suggestions based on what we've seen in previous videos. Find the zeros of this. That's all the directions say. Find the zeros of this. Now, what do we have at our disposal? Well, we have the rational zero theorem, which says I can make a list of things that might work. We have synthetic division and the factor theorem at our disposal. That says if I find a zero, I can make a factor and I can get the other factor using division. And we have Descartes' rule of signs. There's actually another gimmick that I was taught when I first saw this in Algebra 2 and have never seen again. If it happens to show up, I'll mention it. Otherwise, I wouldn't worry about it. All right, so how would we begin doing this? Well, if we're going to find all zeros, we need to start by listing possible rational zeros. Now you may be thinking this is just like one you did in a previous video. Sort of. It's got another unfortunate twist to it, as you'll see in a moment. But the possible rational zeros here would be factors of the constant term, which is 85, over factors of the leading coefficient. Hallelujah! The leading coefficient is 1. That's the best possible number to have there. Because the only factor of 1 is 1, we will actually have no fractions. Well, what are the factors of 85? Well, if you're not sure how to find the factors of 85, just start with 1, which is always a factor. 1 times 85 is 85. There's a fiesta in the hallway. And, all right, I'm going to do this later. Okay, it's quiet now. I'm good. If it gets too noisy, I'll just stop this video and do it after lunch. I'm not sure why I'm saying that. If I do that, you'll have never known it happened. Just thinking out loud. All right, but anyway, if you're looking for the factors of 85, one thing you can do is just start with 1 and work your way up. Try 2, it's not even. Try 3, that would fail. Try 4. Don't try any even number, this is no longer even. 5 clearly works. 5 goes into 85, I think 17 times. That should be it. Because 85 is 5 times 17, both of those are prime. There's no other factors we could find, because if they did, they would be hiding in here somewhere. So the list of factors is fairly short. From least to greatest, 1, 5, 17, 85. Oops, if I were doing least to greatest, I would have written negative 85 first. But let's just write the negatives next. Now remember, I want to list them all out, because as they fail, I want to cross them out. Now, before we jump into this, let's use Descartes' rule of signs to see if there's anything that we can take advantage of. So according to Descartes, let's see how many sign changes the original function has. There's 1, there's 2, and that's it. So, in the original function, there are only 2 sign changes, which means there are 2 or 0 positive real zeros. All that really tells me is that if a positive number works, then there should be another positive number that works. Well, let's check f of negative x. Now, for that one, maybe we should write it out. So I'm going to rewrite the function and change the sign of every odd-powered term. So x to the fourth plus 2x to the third plus 78x squared minus 116x plus 85. Well, goody, this has two sign changes also, which means that there are 2 or 0 negative real zeros. Now they can't both be 0, as I mentioned in the previous video. If there were no positive real zeros and no negative real zeros, then there are no real zeros. Unless 0 is a 0, but it's not. You can check it real quick. And if there were no real zeros, then none of those numbers would work and we would be stuck. So I know at least one of those numbers is going to have to work. And if it's positive, that means there should be 2 positive real zeros. And if it's negative, that means there should be 2 negative real zeros. One thing I neglected to mention in the previous video, it's possible for these zeros to not be in this list. For example, if we did the quadratic formula and we got 5 plus or minus the square root of 2, those are both positive and they're both real, but they're not in this list. So it is possible that when it says, hey, there's a positive real zero, that doesn't mean it has to be in that list, but it probably will be. Because we don't want to push the envelope beyond anything that we're capable of doing. Okay, so what we know according to Descartes' rule of signs is that there are either 2 real zeros or none, 2 positive real zeros or none, or there are 2 negative real zeros or none. And it could be both. There could be 2 positive, 2 negative, and all of them could be real. Oh, that reminds me, I forgot to mention something about the fundamental theorem of algebra. We'll get to that in the next video. It's on my list. Okay. So this really didn't give us any guidance. If either of these had been 0, we could have wiped out half the list. So it's time to guess and check. Or must we guess and check? Is there anything else we can do to help us find a box number that might work? Well, remember, we're finding zeros. We're solving this thing equal to 0. Didn't we do that in the previous series of videos when we were looking for x-intercepts? Yeah, and if you're wondering why I disappeared, it's because I'm about to pull up Desmos.com and drag the camera down here. When we're finding zeros from a function, that's the algebraic view. The geometric view, the geometric view is zeros correspond to x-intercepts. So, why don't we go into Desmos, or the graphing utility of your choice, put the function in, and see if we can find an x-intercept, because that'll give us a 0. So f of x, close parentheses, equals x to the 4th minus 2x to the 3rd, 2x to the 3rd plus 78x squared plus, I think it was 166, plus 166x plus 85. Well, that's not much to look at. I wonder if there's more to this graph that we can't see. Let's zoom out. We're zoomed so far out that it just looks like a big stick hitting the ground. But honestly, it doesn't matter what the graph looks like because all we were looking for was an x-intercept. And do you see one? I do, it's right there. Well, wait a minute. Not only have I found an x-intercept, I found an x-intercept where it touches and turns. Why is that useful? Well, being an x-intercept at -1 means that -1 should be a good box number. But what does it mean because it touches and turns? That means the multiplicity is 2. That means that factor would show up, that means the multiplicity is even. So it's either 2 or 4. It can't be bigger than 4 because it's a 4th degree polynomial. That means that the factor associated with -1, which would be, there it is, which would be x plus 1, has to have a power on it that's either 2 or 4. Pretty confident it's not 4. So I think that's a 0 of multiplicity 2. Now what does that mean? That means that we should be able to use -1 as a box number not once, but twice. We've already gone 10 minutes. Wow, that's crazy. Oh yeah. Oh well. All right, so based on this graph, we're going to use -1 as a box number, and I think we get to use it twice. All right, let me set the camera back up where it belongs. And because of the length of this video already, I am going to do a part 2 for it. In fact, I think now would be a good time since we're already at the 10-minute mark. So in the next video, we'll resume, and we're going to use -1 as a box number.